Hello to all the beautiful people who is meeting here today for us to talk a little bit about this beautiful subject that is called trigonometry, all right? Within trigonometry today we are going to learn about one of the most useful tools you can think about when you think about trigonometry, which is the sine law. Why is it useful? Because eventually we're going to have to face with a lot of problems in which we're going to have some information related to a triangle. This triangle may not be a right triangle, and that's a situation that is kind of problematic because, of course, all these discussions we have had so far are about the right triangle, but I mean, not everything in life is perfect. No, not everything in life is a right triangle, and this means that sometimes we're gonna deal with stuff that is kind of different to that. So let's talk about some situations in which we're gonna deal with triangles different to a rectangular triangle, and how to find as much information as possible from those triangles using this law that we have here today, that is the sine law. Before diving directly into the sine law, first of all, a little bit of notation, alright? Here we have this triangle, and what can I tell you about this triangle right now is that this is not a right triangle, alright? This is a triangle in which any of its triangles has 90 degrees. So how are we going to label this triangle? We are going to add some specific labels. The first one, or the first step, is that we are going to label to label, sorry, the triangles. How are we gonna label them? We're gonna use capital characters, and we are going to label them as capital A. Let's call this one here capital B, and this one would be capital C. After we label the angles of the triangle that we have there, we are going to label its sides. So here we have this angle A, and the opposite side to the angle A that we have in this position would be this one here. So we are going to represent that opposite angle with the lowercase a, in order to point that this lowercase a is representing the length of the segment BC. So this one would be the side lowercase a. The same would happen with the opposite side to the angle B. In this case, we are working with, or we are observing the triangle from this position from the angle B, and this means that the opposite side to this angle B would be this one here. So I'm going to label this as B, and this lowercase b is representing the length of the segment AC. So this one would be our side lowercase b. And then, following the same line of thinking, we will have that the opposite side to this angle C that we have in this position would be this one here. So we are going to call it lowercase c. This is a lowercase. Unfortunately, it's kind of difficult to distinguish between the lowercase and the uppercase c. But anyways, trust me guys, this is a lowercase c that represents the length of the segment AB. So at this point you may be wondering, all right, so well, that's what we have, but how is this related to the sine law? And mainly, what is the sine law? Basically, the sine law is a law that relates the values of these lengths and the values of the sines of each one of these angles with each other. All right, so we are going to state the sine law in a first step, and then we are going to prove how it works. The sine law states that if we take the length of the side A, lowercase a, remember that the lowercase a side, and we divide that stuff by the value of the sine of the angle A, capital A, that represents that angle, that stuff is going to be exactly, or is going to return exactly the same value as the value of the side B, lowercase b, divided by the sine of B, the sine of this angle that we are having here. And then this stuff is exactly the same as the value of the side C, this one here, this one that we have down here, divided by the value of the sine of the angle C. uppercase C, this angle over here. This law that we just stated over there works exactly the same if we work with the inverse version of these fractions that we have here. So we can rewrite that stuff as the sine of the angle A, this one that we have here, divided by the side A, the opposite side to that angle, is equal to what? To the value of the sine of the angle B, this one down here, divided by the length of the side B, lowercase b down here. And this is the same as saying sine of the angle C divided by the value of the length of the segment AB represented by the lowercase c. So this is the statement of our sine law. Now, here comes the question. Teacher, is this true? Should I believe in this? And the answer is no. Remember, you cannot never ever believe in no one in life. You can just believe in the proof, in the mathematical proof, in the mathematical demonstration, because that's how life is, all right? So now our mission is proving that this statement that we have here enclosed in this blue square is actually true. So let's do that. To demonstrate our sine law, here we have these two Cartesian planes. And in these two Cartesian planes, I have these two triangles that are a reflection of each other. I mean, both of them are the same triangle. The thing is that this is like a mirror image from each other, but both of them have the same dimensions. I drew those two guidelines in the middle of the triangle just to observe that you can convert any triangle you want into two right triangles, all right? That's something that can happen, and we are going to use that possibility in order to prove our sine law. Now, some labeling. This is gonna be our right triangle here, and this one is also another right triangle. We are going to start with this one. This angle here is going to be called A. This one we are gonna call it B. This one is going to be our triangle, our angle B, and this one is gonna be C, capital C. Remember that. And now, as this is a mirrored image, this point here represents this one here, so I'm gonna write a B in this position. This one then would be A, and finally this one up here is gonna be C. Also, we are going to add an additional label that is gonna be this one here for this point that we are going to represent as D. As you can see, I put those D's in both triangles. What is the cool thing about converting these two triangles into four triangles, actually into four rectangular triangles, the two that we have here and the two triangles that we have here in this position? What is the cool thing about that? This is that now we can study this line that we have here, this segment SAC, as an hypotenuse, all right, for this triangle, for example, ACD, or for this triangle BCD. So we are going to add the correct name to this stuff, and following the nomenclature that we created for our triangle in the last step, that was this one here, we are going to call this hypotenuse that we have here in this position lowercase b. I propose you to do that. And then this hypotenuse that we would have here in this position would be named how? Yeah, if you screamed A, lowercase a, this means that you are following this video, and that's something that's great. Now, about the sine of A, the angle that we have here in this position, what we can say about that angle? That sine is going to be equal to this opposite side that we have here represented in blue, divided times what? Divided b, that would be the hypotenuse. Remember, sine is equal to opposite side divided by the hypotenuse, or sine in trigonometric language is the value of y divided by r, that would be this b in this case. So let's state that as the sine of the angle A is equal to what? To the segment CD, this one that we have here, CD, divided by what? By the segment AC, which at the end is the same as saying that this stuff is equal to CD, this line that we have here, divided times what? Times the value of B, because remember that AC receives actually the name B. Now guys, let's focus just in this term that I have here and in this rational expression that I have there in that position to create something that represents the value of CD just in terms of these two elements that I have. If this is dividing in this position, this means that I'm going to pass it to the other position, multiplying, and I will have B times the sine of A, that is equal to what? That's right, to the length of CD. Now let's do something similar with this stuff here, but now we are calculating with the sine of B, that is the angle that we have here in this position, sine of B, that is equal to what? Is equal to the segment CD, that is the opposite side that we have represented here, CD, divided by what? By the value of BC, this length that I have here, BC. And that at the end, remember, is that CD divided by, what is the name that we gave to the segment BC? This was A, so I'm going to write here lowercase a. And now, as I want to create an expression that is represented, or is an equation that is created only considering these two elements that I have pointed here, I'm going to say that A, this one passes to multiply to this side, multiply what? Multiply the sine of B. This stuff is equal to what? To the segment CD. Now observe that this expression B times sine of A is equal to CD. And also this expression A times sine of B is equal to CD. What does it mean? That we can combine them together in an expression that is representing both situations, that goes like this. B times the sine of A is equal to what? To A times sine of B. We got that. Beautiful, amazing, interesting. And remember, guys, that math is pure magic. It's pure, yeah, is out doing crazy tricks. Our trick now is that we are gonna make, or we are gonna create two combinations of fractions. The first one is that if I take this sine of A to divide to the other side, and I come with this sine of B to divide to the other side, I'm gonna have the following. I'm gonna have B in this side that is being divided by the sine of B, capital B, and this stuff is gonna be equal to what? I have A in this side that is going to stay there and is going to be divided by what? By the sine of capital A that passed to divide to the other side. So I'm gonna have sine of capital A. And I created an expression that actually represents my rule. But also we can use this original expression that I have here to prove that the inverse expression is also right. Because what I can do is that I can keep my sine of capital A in this position, sine of capital A, and I can take this lowercase a to divide to the other side, divided A. And this is gonna be equal to what? To this sine of B that is staying over there. I am not going to move it, sine of B. And this sine of capital B is going to be divided by what? By this B that I have here in this position. So this is going to be divided by lowercase b. And in that way, what I'm doing here, I am creating the second part of my demonstration, that is this one over here, that says that basically the inverse of these expressions also apply for the same rule. So what is cool about this? We proved our rule. We could do the same procedure putting C in the origin of our Cartesian plane, and we can do the full recalculation, but I mean, go ahead, don't stop yourselves. But what I can tell you is that you're going to have the same result, the same proof. These three expressions are going to return similar results, or basically are going to be the same, and this is why we call it the Sine Law. Now, in which context may I use, or should I use, the sine law? Let's consider the following example. Here we have this triangle, and in that triangle we know two of its angles. Let's number them as A here in this position, B here in this position, and C here in this other angle. Also, let's say that we know one of its sides, that is this one over here, that is 12.5. Now let's start thinking about what we don't know about this triangle. The first thing is that we know what is the name of this side here, as it's the opposite side to a capital C angle. This means that this one is going to be equal to a lowercase c, sorry, my mistake, a lowercase c, that's a lowercase c. And that also means that this side over here is the one that is the lowercase a, and this other side here in this opposite side to the angle B is gonna be lowercase b. Also, something that we already know is the value of this angle here, and you may wonder why do we know the value of that angle? And I will remind you this rule that says that the addition of the inner angles of a triangle is going to return how much? 180. So that being said, this means that we can use our fancy calculator, and we can write the following: 180 minus 75 minus 35, and this is returning as 70. So this means that the value of this angle B is equal to 70. Now, what are the only two unknowns that we have left in this triangle? The only two unknowns are the length of B and the length of A. So we are gonna find them using the sine law. How do we apply the sine law over here? Easy, very easy. Let's start looking for the value of B, let's say. So we have that B is that length divided by what? Divided by the sine of a capital case B, this angle here. So this would be a sine of 70. And that stuff is equal to a lowercase c, which is 12.5, being divided by the value of the sine of 35, that is the value of the angle C. As we stated that, now the only thing that we have to do is jump back to our calculator, and in our calculator we state the problem as we have it. But before doing that, let's do a previous step, that is basically clearing that B, of course, necessary. That B is equal to what? To 12.5, that is the numerator that I have here, times what? Times the sine of 70 that passes to multiply to the other side, times the sine of 70, divided times what? Divided the sine of 35. Now we can go to the calculator and we just introduce the formula that we created, and this goes as follows: fraction, and in this fraction I'm gonna write 12.5 times the sine of 70, and all this divided times the sine of 35. That is the one that I have down here, and I got an error. What is the error? I didn't close this parenthesis, and I have 20.47, let's say 20.5. And I have that the solution to the question, what is the length of my side B, is that the length of this stuff is equal to 20.5. We proceed in the same way for A, so we have that A divided by the sine of what? The sine of 75. 75 because it's the uppercase A, all right? So this means that that's the value of the angle A. Is equal to what? We can choose any one we want, but I usually always prefer to use the original data of the problems, so I'm going to go with C again. So lowercase c, that is 12.5 divided by the sine of 35. So I have that A is equal to 12.5 times the sine of 75 that passes to multiply to this side, divided all this stuff by the sine of 35. Calculator, and we have the following. Actually, I am gonna use the same formula that I was using for the previous calculation. I am just changing here the 70 by the 75, that is the value of the angle that I am using now, and I got a 21.05. Let's say it was a 21. So lowercase a is equal to 21. So yeah, that's the value of our side, lowercase a, 21. And in that way, as you can see, we got all the answers, or we solved all the unknowns from this triangle that I had over there. Just one more application of this stuff. Let's consider that we have this triangle ABC, and now in this triangle we know the value of the angle A, that would be equal to 110, in this case 110 degrees, and we are going to have the value of lowercase a, that this lowercase a would be equal to 9.4, whatever, centimeters, millimeters, foot, if you want, or whatever you can think about. And this segment AC, that is lowercase b, is equal to 6, let's say. So what are our unknowns? Our unknowns in this case are the angle B, the angle C, and also the value of the lowercase c. All this stuff are things that are unknown, so let's find them. In order to find the value of lowercase c, it's necessary to find the value of the angle C, capital case C. How are we going to find the value of that angle? We are going to use the following relation. We know that the the sine of uppercase C divided by the lowercase c is equal to what? To the sine of the angle A divided the side A. But kind of problematic at this point, because we don't have the information near about the value of the capital C or the lowercase c. So what is a necessary route in order to get that stuff? A necessary route is to find the value of B. If we find the value of this capital B, this means that we can use 180 minus 110 minus something to get the value C. So let's do that first. So we have that the sine of B divided 6, that is the value of lowercase b, is equal to let's use a capital case A, sine of A divided by the lowercase a, that is 9.4. We clear the sine of B, and we have that the sine of B is equal to the sine of A, that is 110, I didn't write that, sorry, 110 degrees, times this 6 that was here passes to multiply in this other side, divided by the 9.4. We go to a calculator and we have the following. The fraction, sine of 110 times 6 divided 9.4 is equal to 0.5998. Now here I can do the following trick. B is going to equal to the inverse sine of what? Of this stuff that I have here, 0.5998. And remember, the inverse sine, I get to it through the shift key in this calculator. Remember, it could vary a lot depending on the calculator. Inverse sine of 0.5998, I close this stuff and I get this 36.85. So let's call it 37. So this 37 degrees is the value of the angle that I have here, 37 degrees. And now I can use the following trick: 180 degrees minus 37, that is the thing that I just found, minus 110, that is the value of this angle A. This stuff is equal to what? To capital C. Technology makes us this lazy. 180 minus 37 degrees minus 110 is equal to 33. So first of all, 33 degrees is equal to capital C, and these 33 degrees would go in this position over here, 33 degrees. So I completed my triangle. What is the what is the only thing that I am missing in this moment? I am missing the lowercase c. How are we gonna find it? I wouldn't recommend to use this anymore. The one that I would recommend is using directly lowercase c divided the sine of capital C is equal to, I can use any one of them, but remember, I always prefer to use the original data in order that if I have a mistake, the mistake is not that big. So lowercase a, that would be 9.4 divided by the sine of a, that is 110. Then I clear this stuff. Let's continue a little bit over here. And I have that C is equal to 9.4 times the sine of the angle C, that is 37. We have it here. And all this stuff divided times the sine of 110. And using the calculator, I have that lowercase c is equal to, this one here is equal to 6.02. So this length of c is equal to 6.02. And as you observe, using the Sine Law, we completed all the unknowns of the triangle that we had. So well, I hope you enjoyed this video as I enjoyed making it, and see you in the future in another class. Goodbye.